Hello everyone, I am Aditya Dhawale and I am going to discuss our work on efficient parametric multi-fidelity mapping using Gaussian distributions as structure primitives. Mobile robots such as aerial vehicles are size, weight, and power constrained, which impose restrictions on the computational resources and the memory available on board, thus imposing additional challenges for real-time performance of mapping algorithms. Voxel Grids is the most commonly used map representation in the robotics community. Varying the voxel sizes enables the user to represent the world at varying information fidelity. However, at small voxel sizes, voxel grids have a large memory footprint and therefore do not scale as the size of the map increases. And at larger voxel sizes, this map representation has a small memory footprint but is not capable of reconstructing the world at high accuracy. Gaussian mixture models have recently been proposed as an alternative mapping representation that is capable of representing the sensor information at high accuracy with low memory footprint at multiple resolutions. These approaches typically employ an expectation maximization routine to fit the parameters of a GMM. EM is, however, a computationally expensive algorithm, and the final parameter estimates depend highly on the a priori provided parameter initialization, which is typically not available in real-world scenarios. In this work, we propose a joint hierarchical mapping framework using Gaussian distributions as structure primitives that requires low computational resources, low memory footprint, and can reconstruct the 3D world with high accuracy. The key insight behind our work is that depth measurements obtained from commercially available 3D sensors are spread along the surfaces of objects in the scene. Therefore, they can be approximated as locally planar regions. We want to fit Gaussian distributions such that they approximate these locally planar regions in the 3D observation. We proceed in the following way. Given a depth observation, we divide it into a fine grid of small image patches. In each image patch, we perform the well-known region growing algorithm to find the largest planar region. This planar region is then approximated as a Gaussian distribution. A succinct and accurate 3D representation of the world is generated by performing this operation in each image patch. Repeating a similar process with a relaxed definition of planarity in larger image patches enables us to fit larger Gaussian distributions at higher hierarchical levels, thus generating a highly compressed 3D map of the world that can still reconstruct the world with high accuracy. Here, we demonstrate our mapping algorithm on the augmented ICL NUIM dataset. As sequential sensor measurements are obtained, the global estimate of the map is iteratively refined with novel and overlapping information. Noisy Gaussian distributions are removed, and the incremental updates are propagated throughout the hierarchical levels in real time. Here, we show a brief quantitative comparison of our approach with state-of-the-art mapping algorithms, Octomap and EntityMap, on a few real-world datasets. We vary the resolution for both Octomap and EntityMap between 1 cm and 50 cm. Our proposed approach has lower reconstruction error at all three hierarchical levels than both Octomap and EntityMap, and also has a smaller memory footprint than these approaches for asset reconstruction accuracy. Entity maps are computationally inefficient to fit, and although Octomaps are more efficient than our proposed framework, our approach operates at approximately 18 Hz on a desktop grade CPU, where standard RGBD sensors often operate around 30 Hz. In summary, we propose a mapping framework that is quantitatively and qualitatively superior to state-of-the-art mapping frameworks, is more compact, computationally efficient, and can operate in real time on a CPU. Thank you.